So what we'll do now is we will use the Vega tool to build simple model, linear regression model, so that you get acquainted with the interface, which is a bit tricky sometimes. And then we'll build neural network, and then we'll also use neural machine to build the same neural network and see, because neural machine allows you to animate and to display results in a bit better fashion. But Vega, beauty of it is that it has so many algorithms implemented, and also you can download packages which would add additional algorithms written by other people. And it's written in Java, so it will run on different operating systems, and it's free. So it would be advisable package to start with if you want to start doing machine learning, and you don't have much experience in Python or MATLAB. So that because it's software all implemented, you don't have to code anything, and most of the functions are there. However, if you want to do sophisticated analysis, nice visualizations, you have to move to other packages. By the way, Google, in the Google Earth Engine, it appeared it used Vega. Maybe they use now different tools, which they developed or bought, I don't know, for pattern recognition. They used Vega initially in the Google Earth Engine. That's amazing, but okay, fine. That was when it was just starting 2 years ago, I think, or 3. Okay, so what we do is this. We would first find the exercise which is called DDM exercise Vega 1, LR, linear regression. You have it? That's the file, PDF file with the text of the exercise. It starts like this. I'm using doc file, but you have PDF file. Yes, you have it? Good. That's one thing. So keep it open because we'll follow this text. And at home, if you want to, if you want to master something, you have to repeat it at home again, yet another time, but by yourself. Then you will remember. Otherwise, it will go. So also advice to do same with all the lectures. Review them again, going from slide to slide, then you will remember a bit more. But for exercises, that's for sure. If you do it yourself, then you will master more, of course. Okay, that's the text of the exercise. Second thing we do, I have asked you to install Vega on your laptop. You did it? Wonderful. So then what we do, we find it in the menu of Windows. So it's installable software. And you run Vega 3.8. Yes? You have it? Good. So it starts first a small program that would activate another program which is called Explorer, and actually we'll be working all the time in this Explorer. Come on, it takes some time. Yes. So Vega actually, it's this bird with, they say, colleagues in New Zealand say, it's with very inquisitive nature, so it's learning everything. And Vega stands for knowledge, Christ, I forgot. No, I can't remember. It stands for Waikato. Yes, Waikato Environment for Knowledge Analysis. Thank you, yes. Okay, that's what they say. So you could, by the way, go to the website of Vega. You just type in Vega, Waikato, whatever, and you come to their website. There is a lot of material, help files, examples, downloads, links to other packages implementing different software. So this community lives. So it started, I think, 20 years ago maybe, and this software was written by PhD students in this University of Waikato in New Zealand. For some time it was not really well supported, but somehow then community was developing, and now there is a worldwide community supporting, and it's reasonably bug-free, because the first versions were not always, there were some bugs, and even our students found some bugs in it. But now I think it's much more reliable than before. So please click on Explorer. It's a bit slow, isn't it? But Java is always slow. What's happening? Maybe it loads the whole Java engine. Yes, okay. So there are a number of tabs here. So if we go to the exercise, which I will try to keep here also open. Okay, we did it. Yes, but I first have to introduce a problem to you, isn't it? Sorry for that. So the problem is this. Have you read the exercise, these first pages, which introduces the problem? No? Come unprepared. Okay, anyway, but however, I didn't ask you to do it, so I apologize. So, right, but in brief, 5 minutes. So the problem is to build a rainfall runoff model for a small catchment in Italy. It's located in Tuscany. There are a couple of maps here showing this catchment, and for us it's important, so you can read more details. You find actually this catchment was very well studied by Italian hydrologists. There's a lot of information on the internet about the physical properties and all this. You can find it all on internet. I will not spend time on this. What we are interested in is the data that we have about this catchment. So this is the data on page 5 of the exercise. You see the data here. It's in the lecture notes as well. This plot is not first time you see, I suppose. So what kind of data we have? This is hourly data collected for approximately 3 months. In 1963, all data. And on top you see rainfall. And rainfall leads to increase in flow. You see? Okay. So we want to build a model that would link rainfall and runoff. And we did it once. You remember TankX model? That's the model that you can build easily using this data and calibrate it, as we did. So again, one way of doing this is using lumped conceptual model. It's a small catchment. You perhaps don't need distributed model. Using this data, you can easily build a lumped conceptual model, and it will work. But our exercise is in data-driven modeling, so we will build an alternative model using linear regression, also model 3 if we have time, but for this exercise I excluded model 3 from the consideration, and we will then build a neural network model which would link, again, rainfall and runoff. That's called the rainfall runoff model or hydrological model. So for training, we will use this part of data from approximately 300 point here to the end, 1854, that part, last part. And for verification, we'll use the beginning of the data with the 300 points. question to you, is it fair, such split? Is it statistically similar? No, not terribly, because you have here in training data extremely high peak, and it's only one. We have other 3 or 4 peaks of half of it or 1/3 of it, and we had to make choices where to pick up the training data. So verification data or test data is good to, again, to pick up in such a way that statistically it would be similar. So number of peaks in it would be approximately the same as in a training set. So you can, of course, suggest other ways of splitting this data. For example, maybe taking this part for verification in the middle and left and right hand side for training. But then you have break in the hydrological regime, isn't it? So you continue, then there is a break for if you take out data for verification, and then it starts again. So it's always a problem. So it's good to take the part of the data which is contiguous, starts and ends, because then you would keep the state variables intact, soil moisture. So the decision was made to take this first 300 for verification, the rest for training. So total number of records for training is approximately 1,800, and for verification 300. Now, what variables now we will use? You remember that figure when we discussed how to build rainfall runoff models? It's the same thing. We will try to use, we have to use rainfall. What we have? Rainfall, evapotranspiration, which is subtracted. So we talk about effective rainfall. That's why it's called here RE, R effective, RE, effective rainfall. So evapotranspiration has been already subtracted from this rainfall. I say rainfall, but I mean effective rainfall, okay? And Q. So Q is measured at the same point, so at the outlet of the catchment. So we use Q, previous values of Q, to predict future values of Q, and we use previous values of rainfall to predict future values of Q, of discharge. This is what is written in this formula here on the screen. So function F would be either linear regression or neural network, and inputs would be that many inputs. Now, you remember we discussed that we have to choose the optimal lags. So if you would be doing this exercise again, you please do it as it is explained here. I will not do it. It's a bit lengthy procedure to work with Excel, moves, columns, and all this. So I will explain you what I did for you. So I prepared data set for you already, but advises to do it yourself then at home. So there is no sense of using all these variables. We could, but there is no sense. So what we will do now, we will discuss how to choose the relevant variables out of all these possible lagged rainfalls and lagged discharges. Is it clear what is lagged means? Lagged? Yeah, so we take values of the past. So we could take RT minus 5, so it would be rainfall 5 hours back. It means it's lagged. There is a lag. So what we did in this exercise here, you see this table generated by Excel. And this table shows correlation coefficients when we calculate it for the following time series. One time series is QT plus 1. This is what we will be predicting. So we first build a model to forecast T plus 1, so discharge next hour. And we compare this with, so it's this QT plus 1, you see this column, this row. And we calculate correlation coefficient between QT plus 1 here and RT. So it means rainfall now. RT minus 1 rainfall 1 hour back, RT minus 2, RT minus 4, and so on, RT minus 7, RT minus 8, RT minus 9. Okay, and we stop here. So what we did, we put simply this data into a plot, its correlation coefficients, and what you get is this. So this plot shows correlation between Qt plus 1, it's the value you want to predict, and RT minus I, where I is here. So first value shows, again, correlation between Qt plus 1 and RT. This is RT minus 1, RT minus 2, and so on and so on. You see there is some maximum. All values are high enough, but there is a maximum here. What does it mean, this maximum? It means that correlation coefficient between Qt plus 1 and rainfall 6 hours back is maximum. So, in other words, if you take RT minus 6, it would be the most relevant variable to use as the input to determine Qt plus 1. So this delay of 6 or 7 hours is in fact what we observe. Let me see if I have this plot. What we observe in when we look at this. You remember this? So what I took, this is one of the peaks in discharge, and this is previous peak in rainfall. It's one of them. And if you look at this distance, when discharge reacts to a maximum peak, it will be also around 5, 6, 7 hours. For different peaks, it's slightly different. Why? Because this is average, aerial average rainfall, so it may happen upstream, downstream, and so on, so it's average. But functional dependency is clear, that increase in rainfall leads to increase in discharge 5 or 6 or 7 hours from now. That's physical property of the catchment. And this is how we use notion of physics or knowledge of physics of the catchment or hydrology of the catchment in building data-driven model. So some people say it's black box model. Okay, you can say it, but you have to put some physics into it. And this is how we do it. Choice of relevant variables is very important. It's called input variable selection. That's what they describe the process, input variable selection. You can do it different ways. Here we did it using correlation coefficient and visual inspection. Visual inspection is always useful because correlation is average measure across everything, and here you just see clearly that physics is like this. Increase in rainfall, increase in flow. Okay, is this clear? Yes? I hope so. Maybe there is some difference. Is there?
Yeah, because the plot usually have a bigger correlation coefficient in the RT.
Yes, actually I noticed this, yes, when I was talking 5 minutes ago. Thank you for pointing this out. I'll check. Why is that? But if you do it yourself, maybe you could discover what is the right thing. Indeed, you're right. So here you have 52, 59, 66. It reaches maximum at somewhere here, 75, right? Yes, and in the table, it's also 75 here, is it not?
Yeah, but in this case, in the table is RT minus 5, and the plot is RT minus 6.
Well, I don't know if you can distinguish differences here between 5 and 6. They're hardly noticeable. But I suppose RT minus 6 has the maximum, and yeah, here it's slightly lower. Yeah, I'm not sure. So maybe it's shifted by 1 step. I'm not sure. You're right. So, but on the plot, yes, indeed, maybe this point is slightly higher. But look, differences in the third significant digit, so maybe there was some round-up error or something like this. I'm not sure. Anyway, but this plot more or less correctly reflects this table, isn't it? So, but initiative should be punished. You know this statement that initiative should be punished. So you came up with the initiative to question this data. Punishment is for you to go back home in the evening instead of barbecue and to recalculate all this. And then tomorrow you could present to us if maybe there is an error, and would be happy to see the better results. Do you agree? No, look, I don't want to discourage you to pose questions and to detect omissions in the slides. But thank you for noticing this. Excellent. Yes, you are right. There is some tiny, tiny difference. I wonder why it happens. Yeah. Yeah, perhaps you are right. Maybe indeed it's a plot with QT and not QT plus 1. Yeah, you're right. Thank you. So it should be QT here. But in fact, we want to find correlation with QT plus 1. They're almost the same, slight difference. But this plot would be, the title of this plot is correct, because we have to look at QT plus 1. We want to find relatedness to the variable that was forecasting. Because later we'll be building models for QT plus 3 and QT plus 6. 3 hours ahead and 6 hours ahead. And then you have to look not at QT, but at these variables to be forecasted. You're right. I think it's that shift. Yeah. Thank you for noticing this. I will correct it. Okay. So then now, what is autocorrelation? Do you know what this autocorrelation is? So autocorrelation is correlation of value now in the time series with the value at the previous time step or two time steps back. So if we calculate this correlation, so correlation of time series with itself is 1, obviously, but with the shifted time series 1, so it's discharge here. With the shifted time series is a bit less than 1, but very high. What does it, and then it goes down, but still it stays very high up to 5 time steps, and then it goes down to 0.4 here. Okay, what does it mean? It means discharge is highly autocorrelated time series. It means it's very easy to predict discharge, and you should say discharge next hour is the same as now. And you will be absolutely, almost absolutely correct. In this case, maybe there is no need to build a neural network model or linear regression model. It's called naive model. Notion of naive model is important. So naive model in time series analysis is the model which says that y, if its output t plus 1, is yt. Naive model. And if you are building, okay, let's put it here, t plus capital T, because we're forecasting at some time horizon. So if you are building data-driven models, always first build this model and check how good it is. It's called naive model. Always you have to compare to this. Next step is linear regression model, where you think much more than this, and then you build non-linear regression models. That's the sequence. If you publish a paper, if you don't compare to a naive model, then your paper would be rejected, perhaps, if it gets to my hands, at least. So, very easy. And here, naive model works very well. But how do we assess performance of naive model? We use root mean squared error, or some mean absolute error. So it's mean error, right? So we look at the time series, and we average these errors across the whole time series. Same for correlation coefficient, by the way, because it's averaging across the whole time series. So naive model could be accurate. Why? Because most of the time series works like this, and then sometimes you have peaks, but there are only 5 peaks here. So 5 points where it may not be accurate, but other 1,800 points, naive model is accurate. So if you calculate mean error, it's low. That's why this model is good. But it's good for moments when we don't care. Flow is low, there is no flood. Why should we care too much? We want to predict beginning of flood. And when flood starts to begin, naive model is very bad because it gives phase shift. It doesn't know that rainfall has been coming 5 hours back and water flow should increase. It doesn't know this. It says that flow next hour or in 6 hours is the same as now. And it will be wrong in the beginning of the peak. So naive models always have, so if this is observed, naive model always would have phase shift like this, always. And here, if you calculate this error, it's quite high. That's why naive model are not good if you want to judge about extreme events. On average, nice, yes, but it's not what we want in the end. However, if the model knows about rainfall, then it would already take this into account and try to follow rising limb of the hydrograph much closer. So if we're training neural network, then still we put, care should be taken about the following, that if you put all the variables from, look, if you put all these autocorrelated variables into the model as input, qt, qt minus 1, t minus 2, and so on, you will have a reasonably accurate model, even if you remove rainfall, on average, mean error. But it would be autocorrelation model, and that's not what we want to predict peaks, okay? That's why we include rainfalls, and we don't include all these variables which are highly correlated. Because to say qt minus 2 is almost the same as to say qt minus 3, because they're almost the same on average. See? So that's why after this analysis, we would come up with the model 1 with 9 inputs. You see it on the screen now. It's page 8. It has rainfalls from RT to RT minus 5. You could include RT minus 6 as well, but this is what we decided to do. And 3 discharges now, 1 hour back and 2 hours back. That's so-called model 1, and we sometimes do exercise with this model 1. But for this exercise, I thought it's too many variables, so I suggest to reduce number of variables, because we want also parsimonious models. It means simple models. So we are left with these exercises, with these input variables, RT, RT minus 2, RT minus 4, RT minus 5, so 4 rainfalls, and QT and QT minus 1. Why it's good to have 2 variables, QT and QT minus 1? Because they would show the change in Q. Sometimes instead of QT minus 1, for you to know, we could use delta Q. It means change between QT and QT minus 1. Very useful thing. Our colleague Tony Mintz in '96, they published a paper where they have shown that using delta Q instead of QT minus 1 works better. Not always, however, so up to you. Neural network in principle automatically would discover the difference between them, but sometimes it's useful to put differences explicitly because it's a derivative of Q. It's rate of change of Q, very important thing. If Q changes fast, it would be a signal for this also to change fast, okay? Same for rainfall. Also, sometimes it's useful to put deltas here instead of so many values. But okay, you can experiment if you want. But for this model, whatever you do, it will be accurate because it's very simple model to predict 1 hour ahead. If you predict 2 hours, 3 hours, 6 hours, then it's becoming more complex, then it has sense. But this is deliberately simple model just to understand how it works. So what we see here is a rainfall runoff model. Rainfall input, runoff is output. But it also uses Q as input. And remember, in conceptual model, there is no Q as input. There was only rainfall. It generates Q. You remember lumped conceptual model, tank model? Input is only rainfall and evapotranspiration, so effective rainfall. So this is maybe not a fair comparison because this model uses autocorrelation with Q, which is very strong signal. So if you want to compare this model to a lumped conceptual model, this model perhaps would win always. So such data-driven model would be more accurate than physically based model, conceptual model, because we use information about Q. But you have to also take into account, in reality, sometimes we don't have measured Q on time, not every hour. Maybe every day while this data is sent, but it's not always the case. So if you don't have it, then you have to work only with rainfall. Okay? So be aware. So if you're building this model, you should be sure that in operation, in real operation, you would get data on Q coming regularly to the computing center to run your model. That's an important thing. Of course, for training, we have all this data, we're happy, but what about operation? You have to think about this. Yes? Okay, so then, well, this part of exercise describes how to take data in Excel. So let me show you quickly. We will not do it. So actually, our participants start with the data, which is called CEVA original. It's this data, effective rainfall and Q. That's it. It's in Excel. If you open this Excel file, advice to you is to go through the exercise of arranging data. So what I did here, I would then create a column RT-1, which would be this column shifted down by one step, okay? RT-2, and so on, same for QT. It would create a matrix of data with the columns being this time series shifted, because it's T-1, T-2, and so on. And then you save it as CSV file, and in the end, sorry, this is what I did, so it's next step. So you see, just a moment. Yeah, so QT, you see 18.09 QT, and QT-1, 18.09, but next time step. So that's what we do. So this data was shifted here. So, and it's arranged in these columns like this. There is no, T, yes. So T-4, 29, and this 29, all this like this, okay? So that's what you want to arrange data. It's easy to do in Excel. In 5 minutes, you can do it easily. But Vega needs data prepared in ARF format. I'm sorry. So Vega needs data to be prepared in this format. So this data came from Excel, saved as CSV format. You see it's comma delimited format. It's the same data as we had before. But Vega wants also metadata about descriptors of these variables. And this you have to do manually. Okay, it's easy. On top. So first relation, it's name of this model. And then you see next block called attributes. And here you give names for this attribute so that they would appear in Vega in all these visualization files. Give them any name you like. And you have to say real to instruct that these are real values and not labels. Very simple. So this is the file we will use now to train the model. So RT, RT-2, RT-4, and so on and so on. Okay? Now, the output is always the last, T+1. This is the output. So this data here, it's the last value here, is for calibration, it's the output. But our model will try to generate data which is similar to this last column here, Qt+1. Okay? Clear? So that's how you prepare data, how you form your case. You take standard time series from Excel or whatever you take it in this form, save it as shift data to create lagged time series, create the matrix, save it CSV, and add headers. That's it. It takes 10-15 minutes. Quite simple operation. Any questions No questions. Good. So let's start with a new model. We go to Vega Explorer and we open the file which I prepared as I explained to you how I prepared that file. So if you click, please follow now me closely. You click Open File button. And Vega always, unfortunately, doesn't remember last folder. That's a disadvantage. Maybe you could instruct it to remember it, but I don't know how. So you have to navigate to your folder where your data is. And I ask you to have a folder which is not too deep in the structure, otherwise you have to jump. So in my case, it's here in D. And somehow Java is very slow to navigate across folders. I don't know why. You click and nothing happens, you see? I don't know what's happening. Is it the same for you? Slow? Look, you see how slow it is? Your Brazilian computers are much better than mine. It's obvious, yeah. So I don't know what you do. What is it? I'm too close to this one? I should move away? Okay, so let me... Sorry, I don't know what's happening. Maybe antivirus? I have no idea. Come on. It's amazing how slow it is. What's happening? Yes, finally. Okay, so our file is called CEV6 inputs train. You have it? 6 inputs. Good. Open. Okay. Finally. So what you see is a list of variables over here. Some basic statistical information on the right about different attributes. You see it calculates some statistics. Okay, not terribly important at this stage. You can also apply some filters. If you want to know more, read about Vega. We'll not do it, but there are some additional things to prepare data and select some data within particular range and stuff like this. What we'll do, we'll go to the tab Classify. So classify means actually to build a model, classification model or regression model, doesn't matter. It's all called classifiers in Vega terminology. Click Use Training Set, because first we deal only with the training data. Because Vega, it's maybe not terribly logical. If you click on Supplied Test Set, it would give all the results for the test set, but not for training set. So first we want to see if training is good. So don't select any test set, just training. And classifier we will use will be linear regression. So please click on classifier, click on functions, and choose linear regression. Okay? Done? Sorry? Yes. Okay, now the output would be Qt +1. However, you can choose another one, but don't touch it. So if it's last one, it always shows here last. So advice is always to have the predicted value in the last column. And if you click Start now, linear regression model has been built. That's the linear regression model. You can see it here. You can save it into a file if you right-click here and say Save Results Buffer. Don't do it, but you can do it if you want. And accuracy is shown here. Root mean squared error is 13, and so on and so on. Now, please note how to visualize the results. It's not immediately clear. Right-click on this line which corresponds to this last run. Right-click on it. And choose Visualize Classifier Errors. So this is the scatter plot. Qt plus 1 predicted against Qt plus 1. Okay, so you see it says on top X is Qt plus 1. This is measured. And Y, this vertical axis, is Qt plus 1 predicted. Okay, this is scatter plot. So sometimes points stay on top of each other. If you want to see them, you use jitter. So if you move jitter, they jump around randomly, but right now you don't need it. For the future cases, when you want to distinguish them, they jump a bit around. So, is it a good model? So scatter plot, if all the data is on one line, scatter plot would be one line, then it's good. Here, not terribly good. Look, even for low flows, you have quite high errors here. See this? Yeah. Could we, now, if you want to save this, you click Save. Let me go to the exercise and see if I don't want to deviate from exercise too much so that you could reproduce. So visualize errors. So when you click on the Save button, you would save all the, so it's not results buffer, you remember. Results buffer is something else. So when you click Save, you will save the time series, all inputs, observed and calculated outputs. Save it into CEVE LR linear regression out -training ARF for future use. Why do we need this data? Because we'll be able to plot it later against neural network output or against observed data and so on and so on. Okay? So we'll need simply this time series to save. This is how you save time series. So let's do it. So again, in this visualize, I clicked Save. And again, I have to navigate for 25 minutes to my folder. So maybe, I don't know, how can I do faster? If I type it in here, what will happen? Dimitri. I wonder if it's faster. Extremely slow. What's happening? Somebody maybe is listening to my computer. Oh, okay, it works. Oh, now it's a bit faster. Not much. Unfortunately, Vega doesn't remember where you were. Maybe there is a way to instruct it. Like in MATLAB, you say working file, and then it always opens working file, but come on. Sorry, for the next exercise, I will move my folder somewhere to C drive. Would be faster. It's amazing what's happening. Right, so we give it a name. What the name I suggested? Okay, this name, okay? Right, let's look into it. I don't see this file. Huh? I don't. It should be alpha, this one, yes. So let's have a look at it. So what you see in this file is all the data, but it has additional column. Unfortunately, it's not the last one, but okay, this is how Vega works, and you cannot suppress this. It's last but one, which is predicted Qt plus 1. That's the output of the model during training. Okay, is it clear? So that's where you would pick up this data to plot in Excel, nice plots, and in whatever software you use later to process this. So we'll keep it for the future visualization. Again, so it's not last, but it's last but one. So, okay, that's what designers decided. That was building the model. So the model is built. Now if we close this window, oops, what did I do? Yes. Let's have a look now at the model itself. Question to you, do you like this model? And what strange things you find about this model? It's a linear regression model. You can read it, you can analyze it. Do you like it? You don't know, think a bit. That's why we're here. This is linear regression model linking discharge and rainfall. Look, in principle, increase in rainfall leads to increase in discharge. And what does this model say? What do you think? Well, but look, we assume it's linear because we said we're building linear regression model. Of course it's not linear, but we assumed that linear regression model would approximate this nonlinearity well enough. Okay, not terribly good, but okay, it's linear because this model is linear. But you cannot deduce from this model that a relationship is not linear. You say because it's high error, so relationship is non-linear. Yes, you're right. So that's true. So you can deduce. But look at the coefficients of this model. Do you see something strange? What? Just a second, he was the first. Yes. For me, and what do you want to say? Yes, is negative. Exactly. That's what bothers me. However, this is the best model you can imagine. It was optimized. And this negative coefficient is against your understanding of physics. So this says, strangely, that t minus 4 coefficient is positive, which is normal, and suddenly t minus 1 becomes negative. What's happening? And what's happening, you don't know. So look, multiple linear regression models behave like this. They put strange coefficients here. Why this is 7 and this is 14 and then again 6? Why is that? Why suddenly t minus 2 has much higher weight than other neighboring? We don't know. So, but if you look into the space of this model, look, this model has 1, 2, 3, 4, 5 inputs. And the relationship between this is not always clear. So it appears that if you would put here negative coefficient and here high coefficient, they would somehow compensate each other and lead to a more accurate model. So it's just pure this mathematics and optimization that leads to this strange result. Conclusion, don't expect that building such models would reveal you real physics in it. Some people say data-driven model, after it's built, it would reveal you physics because it would discover hidden laws. But it discovers it wrongly, sorry. So don't try to read into linear regression model. Some people say linear regression gives you a visualization of dependencies. Yes, it does, but it's against your physical understanding. So be careful with trying to read linear regression models literally. Sometimes they give strange results like here. And it's not only in this model, it's many other models, the same thing. So look at them as a sort of black box that gives you accurate results, and don't try to look into these details. However, there were some papers that were even trying to say that even neural network with a nonlinear relationship discovers some physics. Some nodes are responsible for base flow, some nodes for overland flow. I don't trust this. I don't see it. Even linear regression cannot do it. Why neural network would do it better? I don't see it. So, but that's my own opinion. Maybe other people could explain why this is negative and this is positive, and they differ 2 times. I don't know. Right. Anyway, this model is not terribly accurate, but it works, so it gives some answers. So that was first exercise with Vega, and now you know how to save results. And again, if you right-click on this, look, if you run more models, there would be more lines in the results section, and it will remember in memory all this. So you can come back to previous runs and save results. So it's possible. It's a nice feature of it. So it has a bit of history of experimentation. So if you right-click on this and click on Save Result Buffer, you would save this text. But also you can copy it from the screen directly and put it into another file. And for your report, you can put this linear regression model and assessment of error. Okay? Any questions here? No. Good. Another thing is to show it to you. If you right-click here in linear regression, right-click, and click Show Properties, you would see different parameters that would influence how this algorithm runs. Here it's not too much, but on other places you would have many more parameters that you want to change. Okay? And if you click here, so this configuration means this. Look, Vega is built in the following fashion. All these models are implemented in Java code, and this is purely interface on top of some code. So when you run this linear regression, it would in fact start linear regression code and pass all these parameters over here. These parameters which are listed here, you can change either by hand over here. You see, for example, number of decimal places you can change to 5, then it would be 5 here. Or you can do it in well, you can view it in properties. You see number of decimal places here, 4. And if you change to 5, then and save it, then it will run with 5. Okay, so that's access to these parameters in these algorithms. In neural network, it could be important because you can control many things in the neural network and other classifiers. Right. So what do we do now? We saved the results of linear regression model, and we reached actually the end of this exercise. Yes, to test the model. Sorry. Now let's test the model. What do we do for testing the model is this. We save the results of training. Let's forget it for a second. We now click supply test set, and we could specify set test, or you could click on cross-validation, tenfold cross-validation. I will explain to you in a second what it is. And also you can have percentage split. So it means that the first 66% here, or n%, would be taken as training, and the rest would be taken as test. So there are some options for this. But we have test set, separate test set. I prepared it for you. So if you click on it, oh no, it's again slow. What's happening? Look at this. Huh? Is it fast in your case? Okay, jump to your folder, pick up test set, which is called verification, with the same name, with the 300 in the name. You see it? Oh, look, it remembers here. Nice. What happened? Strangely, it comes to this folder now. What's happening? I don't know. Not Q1, because it's 9 input model, but model with 6 inputs, verification, this set. Okay. And now, click start. Vega is still jumping here. You see there is a Vega jumping here. It shows that there is a progress. It eats some food, I think, this bird. Look, this is the result for test. You don't see it clearly here, but okay, so that's what it is. You see here, it says time taken for test set. Now right-click on this second run. So first run was about training, and second run is test. And say visualize classifier errors. Is it different? Is it test? Just a second, let me see. Yes, let's look first at errors. So on training, in the first run, you see root mean squared error was 13. In test, it's amazingly lower, 11. Typically it would be higher, but here it's lower, but close, not that much difference. But relative absolute error is higher, so it's 22%, and in training it was 15%. Okay, so different run, different data set. So that was training. And this is the test. So again, test is also not terribly impressive. You see here large errors here and large errors here. But there is also a lot of data where results are quite accurate in the middle. But for peaks, it's not terribly good. And even for low flows, there is big errors here. Okay? That's what you have. So to save it into, sorry, again, visualize classifier errors. So go to save here. And what you will save now is the results of the test against the calibrated. My Vega again wants me to navigate God knows where. Anyway, save it please into your folder, working folder, and later we'll visualize in Excel and we'll try to analyze what this model does well and what it doesn't. But we'll do it when we have neural network results so that we could show the observed, linear regression, and neural network on one plot. Let's do it later. Sorry, it's very slow. So. And we agreed to use file which is please use this file name, CEV linear regression out verification, okay? Come on. So, done. So now we have this done, but where is it? No. Why it's not here? I don't see it now. Christ's sake, what's happening? Okay, maybe I saved it somewhere else. No. Do you see that? Does it save in your case? Not in mine. Anyway, it should be somewhere. So what we did, we built linear regression model, we analyzed its performance, at least partly, and we learned how to use this software. Maria Clara, when do we stop? We have some time still for neural networks? Yeah? Okay. So what we do, colleagues, now is, yes, let me tell you what it would be useful for you to do. Yeah, this visual inspection of the predictor, but we'll do it later. Assignments. Look, you can do whatever you like with these assignments. These assignments, perhaps not what you all will be doing, but I would propose this. First, to propose structure of the model 3 with less input variables than we have, even less. Reduce number of variables and see how it goes. Verify its performance and all this, do the same thing. Then, what is more interesting, build a model for Qt plus 3. It's a part 2 of assignment. Build the model for Qt plus 3 and see if it works better or worse than Qt plus 1. Because Qt plus 1 is a simple case. It's a very simple model. Qt plus 3 would be not as good as this. And Qt plus 6, which we also can build, would be even worse. But not bad at all. So it's for you then to analyze what variables would be in that model. Start from the very beginning. Take that spreadsheet, CEV original, with 2 columns only. Build up the lagged variables. Think what lagged variables would be inputs to your Qt plus 3 model and Qt plus 6 model. And build these models using both linear regression and neural network, as we will be doing shortly. Okay? So, but start with linear regression because it's easier, it's faster, and all this stuff. Use Excel to build linear regression model and see if it's the same. I don't know. because algorithms could be different, they could be different models. And if it's different, it would be interesting. I don't know, really. So try it. In Excel, you can take it in 5 minutes using the same data set. Just remove the header, and you take the same data set built in Excel. Sensitivity analysis. It's not only for this exercise, everywhere. How to do sensitivity analysis of this model. We'll talk about in the lecture about uncertainty, but already now, what is sensitivity? Sensitivity analysis aims at studying the behavior of the model when parameters or inputs deviate from what was assumed. In this case, you can play with the coefficients in the linear regression model, but it's not terribly interesting. But you could play with the deviations in rainfall. So if you change rainfall a bit by adding some noise, look at what's happening with the output. If it's large change, something is wrong. If it's small change, then it's fine. You can do this as well, but maybe after we discuss uncertainty on Friday. Data transformation. I introduced to you notion of Box-Cox transformation, and we also built this exercise with Box-Cox transform data. Do it yourself. Would be nice exercise. Formula is simple, but if you do it yourself, you'll understand how it works. And then in Excel, you do it in Excel. And in Excel, you plot the PDF of data now for discharge. And PDF, which will be changed, probability density function for the transformed data. And analyze. Maybe this model would work better. Could be. Especially Qt+6 model and Qt+3 model, because this one would be good anyway. Okay? Right. So that was exercise in linear regression, but now yes, save. Now let's move to neural networks. We use the same input file to build neural network model, and we would use the same input variables. I also gave you the exercise on neural networks, which is called ANN6, I think. Do you have it? It's called DDM XR ANN16. I think I sent you the link. You should have downloaded. It was on Monday. Yes? Do you have this file? Oh, I'm terribly sorry. Really? Very sorry. Sorry for that. So somehow it's in the folder files to give. So it means I didn't give it to you. So let me then, I'll send it to you in 1 minute. And I will not use the link, I just sent the file because it's very small. It should be in your email now. Yes? Found it? No? Not in the email. Arrived. Ah, okay, sorry. Take some time. Oops. Yes, done? Or you could follow what I'm doing on the screen as well. So, because files you have already, input files. Okay? So we will move to step 7 actually, building neural network using vehicle tool first, and then we move back to a neural machine maybe tomorrow. We'll see if we can get it done now. So let's go back to Vega. Click Use Training Set again, not to forget. Are you there? And go to Classifier. And choose neural network, which is called multi-layer perceptron. Okay? So first let's analyze these parameters that you see here. If you click on More here, you would have the help file, and it's useful to look into it. Why? Because some of the parameters are codes, not real numbers. So if you look at hidden layers parameter, it's not straightforward why it is A. So if you go here, you would see that about the hidden layers, it's described here. So if you put A, which is default here, number of hidden layers, you remember, it will be automatically chosen by calculating, taking half of attributes plus classes. So classes is 1, so it would be half of the attributes, number of hidden nodes. Okay, or you could set it to 1 simply, and then there will be 1 hidden layer. There is a mistake here. It says list of positive whole numbers, 1 for each hidden layer. So this positive, number is number of hidden nodes in that layer. Okay, so play with it, and you will see that how it reflects on the structure. But let's leave it now as it is here. Then normalize attributes. You see, normalize attributes. It's true, so that when you work with these attributes that to be normalized, please pay attention to these parameters. We'll not go through all of them, but later maybe we have time, we can play a bit with this. Here there is interesting parameter, graphical user interface. It's set to false, but if you set it to true, it will allow pausing and altering the neural network during training. That's an interesting option. I never used it actually, but if you want to experiment with it, maybe it's advisable to do. Typically, it's not needed. Okay, so let's close this and see if it works. So again, we use only training set now to train neural network, and output is Qt+1 again. And let's see what happens now. Bird is jumping, so there is this process, automatic calibration, automatic process is going on. You see nothing, but the process is going on. Stopped. Look at the mean squared error, 5.9. You remember what it was? It was 15. It's 3 times lower. So if we go to visualize, let's see. Look, it's much more accurate model, eh? And amazingly accurate for peaks. See this? So it's you know, surprise. However, for some low flows, it's not accurate, but it's less of a concern. So it's quite accurate model, but we should look, of course, at the hydrograph to see more about this. So here we say save. Please save it, because it takes for me half an hour to save. So save this using words out, ANN, out, and training. It's training, remember. Yeah, save this hydrograph so that we will be building hydrograph. Maybe I save it as well. So name for it would be you can also visualize neural network like this if you want. You can play with number of hidden nodes and so on. So let me save it still. Just a moment, where is it? Come on. So that's a trick. Let me also save the linear regression. And we'll say training again to be sure. Just a moment. All right, so now we have 3 files saved with the output. One is training linear regression, verification linear regression, and ANN training. Let's test a neural network, right? So now we click supply test set, click set, open file, and choose file which is called CEV6 input verification 300. Click start. Bird is jumping. Now testing is happening. Why it's so long, I don't know, but okay. It should be very fast because it's testing. You don't train anything, you just test. Okay, bird is happy now. So let's visualize errors. Not bad at all. Okay, there are some errors here, but okay. Let's save it now. And the name would be CEV-ANN-out-verification.arf. So we have 4 files now. They contain a lot of redundant information, but most important is column which is last but one, which give you predicted values for training and verification. So your job would be to use Excel and Notepad first to remove the header or just import it into Excel. Single out that, use CSV as the input data into Excel, you know, from text file, CSV, delimited by comma and all this stuff. You bring it in, separate these columns, make column, first column should be observed, always. That's useful for all your reporting to have first column observed. Why? Because all modeled would come on top of it. And it's nice to have observed plot which is gray thick, a bit thicker gray. And then on top you will see thin colored lines of models. It's better for visualization. Okay? And then we have two plots. One plot would have observed linear regression and neural network for training, and second plot observed linear regression and neural network for testing. Calculate root mean squared error also in Excel would be useful if you want to display it, and it would form your report about this exercise. So make a conclusion about what is accurate, what is not. And we'll look at it on Monday, not Monday, on Friday, yes, so that everybody would be in on Friday and discuss the results, what is good, what is not. And maybe we'll have more experiments with all this stuff. I advise you also to read a bit more about Vega so that if you have questions, we could discuss them on Friday to somehow, so that you master at least one software to build data-driven models, which is useful. Also, there was a request from you to return back to globe model and to make real case when we would be optimizing some function given by external program. So I'll show you how to do it. But I want to tell you that perhaps advice would be to use MATLAB or Python, where you have much more flexibility than in Globe. Globe is a nice tool for visualization and initial steps in teaching, but when you want to do real experimentation, then you need many more things on top of it. And all these toolboxes are in MATLAB and Python, and Globe doesn't have all these options. But I'll show you how to do it. Plus, on top of it, I would suggest to take these things, this data for the CEV, go to ANN, a neural machine, and to visualize this process of training. Let's see how it goes. Because in Vega you cannot see it. Yes? Any questions? No? Good. So please try to use Thursday in playing with what we learned so far. Maybe formulate your questions. We'll have discussion about these questions on Friday when we could have opportunity to do it. Yes? Right, so requested time I think I respected more or less. We're done for today for the lectures because most of you would leave now to listen lectures on what? On philosophy or mathematics, or what will be this? You don't remember even, but... Huh? You will be teaching. How to teach? Oh, it's very useful. Okay, that's good. By the way, I have also presentation how to write a paper, if you're interested, on Friday. So it's based on my experience from writing papers and explaining to students how to do it. Let me see. And there is also text. I think I sent it to Maria Clara when she was working on her paper. Was it useful? Thank you. What other answer you would expect? This is called How to Prepare a Paper and Dealing with Reviewers. If you find it interesting, from my experience, because I am a reviewer, I am editor in a journal, so I deal with reviewers, I deal with authors, so it's based on my experience. Also, I found some good stuff on internet, creatively modified it, but it's actually what I wrote, and it's 5 pages of... I will send it to you, read it, but we could then, I have also presentation, which is a shortened form of this, and we could then go through this for half an hour, maybe, if you want. You will have to write papers for your MSc, isn't it? I know, in Brazil it's obligatory. No? Paper. But it's nice. I advise you to do it. It's opportunity for you to publish. When you go for PhD or work, you say, look, I have publications, you know, so. Good. Sorry? Again? Right. So what do we do after lunch? And how many people will be after lunch? I don't understand. 1, 2, 3, and what our colleagues in another university? So what do we do then after lunch? Because it's not fair to give lectures to move on when most of the people would be gone. What's the plan? I don't know. So maybe we do nothing, also a possibility, unless you want to discuss something. But I thought it would be useful if everybody is present. Otherwise we have, what, 3 people? Of course we could discuss, I don't know, life and whatever, so. Maybe you have specific questions, I don't know, about your MSc, which is not terribly interesting for others, fine then. But if it's a topic of general interest, I think it's unfair to deprive others from... Up to you, tell me. I'm prepared to do whatever you tell me.